Good morning. My name is Klaudia Lyzinska. I'm from the Warsaw University of Technology, branch in Płock. I will present my research paper entitled Analysis of Presence of Microplastics in Food Products. In recent years, the problem of microplastics in the environment has become one of the most serious threats to human health and the health of the planet. These microscopic pieces of plastic, less than 5 millimeters in diameter, have been detected in water, air, soil, animal bodies, and food products. More and more research indicates that microplastics can enter the human food chain, but their impact on health is still not fully understood. As indicated by the World Health Organization, further research is needed on the mechanism of microplastic absorption and its potential impact on the human body, including the immune system and hormonal balance. One of the most important sources of their consumption is food products and drinking water, which raises serious worries about their impact on human health. A key area that requires detailed analysis is the presence of microplastics in food, both natural and processed. Studies show that plastic packaging can be a potential source of secondary contamination with polymer particles, especially under high temperature conditions or in contact with water. One of the key challenges remains the development of effective and standardized methods for detecting microplastics, which would allow for reproducible results and comparison between studies. Various analytical techniques are used for this purpose, including fluorescence microscopy, often using dyes such as night red, and FTIR spectroscopy. Both methods, despite certain limitations, enable the identification of microparticles based on their physicochemical and structural properties. Previous studies have shown the presence of microplastics in bottled water, fish, seafood, and even honey. In particular, plastic packaging has been shown to have the potential to release microparticles into food through friction, heat, and contact with acids and fats. In light of the above information, conducting research on the presence of microplastics in everyday products such as rice, groats, or tea seems not only justified, but also necessary to evaluate the scale of consumer exposure. It is particularly important the exploration the impact of the type of packaging, for example plastic bags, aluminum foil, paper, and the method of food preparation on the level of microplastic particle migration. Such analysis can provide valuable information for consumers, food producers, and institutions responsible for food safety. The research work used samples of different types of tea, as well as rice and groats from different producers available on the Polish retail market. Tea in bags, rice stored in 3 types of packaging were tested, in foil bags portioned in 4 pieces, in a 1 kilogram foil package, and in a paper package, as well as groats stored in 2 types of packaging, in foil bags portioned in 4 pieces, and in a 1 kilogram foil package. The focus was on evaluating the effect of the type of packaging on the potential migration of microplastic particles into distilled water in which rice and groats were cooked. The effectiveness of 2 analytical techniques, fluorescence microscopy and FTIR spectroscopy, in identifying plastic particles was also compared. During the classification of products, attention was paid to the composition and possible markings concerning packaging. For example, markings concerning the type of material, biodegradability, or contact with food. The work also used a preliminary visual inspection of all packaging to determine their material structure and check whether they contain additional plastic elements. Particular attention was paid to rice and groats cooking bags, the structure of which often contains micro holes and can ensure durability during cooking. All samples were numbered and anonymized before laboratory testing to ensure objectivity and repeatability of the analysis. Samples were stored at room temperature, away from light and moisture sources, until they were prepared for testing. Sample preparation for microplastic analysis required special care to minimize the risk of contamination and to ensure appropriate analytical conditions. Each sample was tested in a sterile laboratory environment. In order to limit the introduction of external contamination, only laboratory glassware was used for cooking, which had been carefully cleaned and rinsed with distilled water beforehand. During the preparation of the research work, all tea samples were prepared by pouring an appropriate volume of boiling distilled water over a single bag, according to the manufacturer's recommendations. The brewing process took place in controlled laboratory conditions using distilled water at the temperature indicated by the manufacturer, and the extraction time was selected as the maximum recommended for a given product. The amount of water used for each single sample was 200 milliliters. After brewing, the tea bag was removed and the resulting infusion was left to cool at room temperature. Rice and groats samples were cooked in 450 milliliters of distilled water, taking into account the maximum recommended cooking time recommended by the manufacturers. After this time, the bags with the cooked product were disposed of, and the remaining liquid was subjected to further analysis. The samples were left to cool completely at room temperature. The obtained water was used for further tests. Two analytical methods were used to detect and identify microplastics: fluorescence microscopy and FTIR spectroscopy. Fluorescence microscopy, especially when using a dye, Nile red, allows for the detection of plastic particles by selectively staining them. This technique also allows for rapid quantitative analysis of particles. In turn, Fourier transform infrared spectroscopy (FTIR) allows for precise chemical identification of microplastics thanks to the characteristic absorption spectra for specific functional groups present in the materials. Fluorescence microscopy allowed to quick and easy detection of the presence of plastic particles. Using a glass pipette, 3 drops of the test liquid were applied to a previously cleaned microscope slide. The samples were stained with Nile red, a lipophilic dye that selectively binds to polymers, allowing them to be observed under a fluorescence microscope. The stained samples were left to dry under sterile conditions in a laboratory dryer at a temperature of about 95 degrees Celsius. Then observations were carried out using a fluorescence microscope. The key element of a fluorescence microscope is the dichroic mirror, which acts as a wavelength splitter. It reflects the excitation light while transmitting the fluorescence light emitted by the sample. The sources used in this type of microscope are usually intense white lamps, so it is necessary to use an excitation filter that transmits only a selected range of wavelengths, for example, blue lights. The dichroic mirror reflects the excitation beam onto the sample fluorophore. The fluorescence is collected by the objective from the sample and then passes again through the dichroic mirror and the emission filter, which cuts off all other wavelengths, leaving only the fluorescence signal reaching the detector, as shown in figure. The second method used was Fourier transform infrared spectroscopy, which allowed for a detailed analysis of the chemical composition of the observed particles. FTIR enables the identification of polymers by measuring the absorption of infrared radiation by the sample, generating characteristic spectra corresponding to specific functional groups in the structure of the molecule. The key element of the device is an interferometer in which the infrared radiation beam is divided into two parts. One of them is directed onto a mirror through a prism, while the other is reflected from the prism and hits a moving mirror. After reflection, both beams are refocused in the prism where the interference phenomenon occurs. As a result of this process, an interferogram is created, which is then recorded by a detector and converted into a spectrum using the Fourier transform. The frequency of the signal on the detector depends on the speed of the mirror and the wavelength of the radiation source. The important aspect is that based on the wavelength, the detector can read the frequency and the intensity of the signal at the same time. The schematic of the interferometer is shown in figure. Microscopic observation revealed numerous particles of diverse morphology. Irregularly shaped fragments and fibers dominated. Analysis of microscopic images using fluorescence microscopy confirmed the intense fluorescence of the tested particles after the application of Nile red, which suggests that they may most likely be microplastic particles. FTIR spectra obtained for the tested samples did not allow for clearly identification of the present particles as plastics. Broad absorption bands characteristic of stretching vibration of OH bonds and bands corresponding to bending vibrations of the hydroxyl group were observed in the spectra. Both bands are typical for the presence of water molecules, which suggests that this signal could have come mainly from the water contained in the sample. The lack of characteristic bands for typical polymers made it difficult to clearly identify the particles as microplastics. Based on the conducted research, it can be concluded that microplastic particles are commonly present in everyday products. The main source of these contaminants may be packaging materials, especially those made of plastics. High temperature during steaming or cooking significantly increases the migration of microparticles into food, which confirms the hypothesis of secondary contamination resulting from the food preparation process. It was also found that the use of packaging made of declared ecological material can reduce, but not completely eliminate the risk of microplastic migration. The result suggests the need from the further research of the stability of biodegradable plastics at high temperatures. A comparison of the applied research methods showed that fluorescence microscopy is an effective method for detecting microscopic particles. The FTIR techniques provide the necessary precision in identifying their chemical composition, which is crucial for a comprehensive assessment of the health risk associated with the presence of microplastic particles in food. The conducted studies of FDAR spectra obtained for the analyzed sample did not unequivocally confirm that the detected particles are plastics. To fully assess the presence of microplastics in food products, it is necessary to continue research, including electron microscopy, or use micro-FDAR. Thank you very much for your attention.